Hello friends, continuing with our previous videos on magnetic effect of electric current. Here is part 4 for you. As usual, we recommend use of earphones for better audio quality and higher concentration. The video will explain a very important phenomena, electromagnetic induction. In short, we write it as EMI, electromagnetic induction. The phenomena is important because it is the phenomena on the basis of which we produce electric current. So, you know the importance of electric current in our life and it need not be overemphasized. The phenomena is as important to us as electricity. And then we will study application of this phenomena EMI. You must have come to know by now that it is used for production of electric current. So, electric generator which converts mechanical energy to electrical energy is based on the phenomena of electromagnetic induction. We know that a current carrying conductor placed in a magnetic field with its direction perpendicular to the magnetic field experiences maximum force. This you have studied in the previous video. You may recall that you have also studied the method, that is Fleming's left hand rule, to find the direction of the current. This force may cause the conductor to move in the magnetic field. Now, let us suppose that we have a conductor moving in a magnetic field, or we change magnetic field around a fixed conductor. Earlier the magnet was fixed, conductor could move. Here it is the reverse condition. The field is changed around a fixed conductor, or a conductor is moving inside a magnetic field. Let us see what will be the effect. This effect was first studied by an English physicist, Michael Faraday. In 1831, that is historical, Faraday made an important discovery that moving magnet can be used to generate electric current. We will further study it by an activity. In the setup, you have a coil AB with a large number of turns. The coil is wound on a non-magnetic roll. We connect the ends of coil to a sensitive galvanometer as shown. Take a strong bar magnet and move its north pole towards end B of the coil. You will find that the moment you move the magnet towards the coil, we get a deflection in the galvanometer. Galvanometer, you may recall, is an instrument used to detect and find the direction of electric current. This indicates that motion of the magnet can produce electric current in the coil, which is indicated by a momentary deflection in the galvanometer. Suppose the deflection is towards the right, which indicates the direction of current. So, there are two things. The moment you move the magnet towards a fixed coil, you get a deflection indicating the production of current. The moment you stop the motion, the deflection drops to 0. It means it is the motion of the magnet which is producing the electric current. Now, what you can do is go in for a reversal of direction of motion of the magnet. Withdraw the north pole of the magnet away from the coil. The galvanometer will again show the deflection, now in opposite direction. You can keep the magnet stationary and alternately move the coil. Means you can move the coil towards the magnet or away from the magnet. The galvanometer needle will show deflection indicating the direction of current. You may move the south pole towards the coil or away from the coil. You may move the coil towards or away from north pole, south pole. In all the cases you will get current. Now, one very important observation which you need to make is that the deflection loss, as long as there is actual relative motion between the coil and the magnet. With the coil and magnet kept stationary, deflection drops to 0, indicating that there is no current. So, this is an activity which gives you a very clear indication that relative motion between the coil and the magnet produces electric current, which lasts as long as there is actual relative motion, and the moment you stop the relative motion, the flow of current also stops. So, let us sum up. We conclude that relative motion of the coil and magnet produces current lasting as long as the relative motion exists. The motion of a magnet with respect to the coil produces induced current, induced potential difference, which sets up induced electric current in the circuit. A convenient way of finding the direction of induced current produced by the phenomena of EMI, that is electromagnetic induction, will be discussed later in the unit. We have made use of a galvanometer. Just a passing reference, a galvanometer is an instrument that can detect the presence of current in the circuit. The pointer remains at 0, that is the center of the scale. We have center at 0, means we have 0 at the center of the scale. So, the galvanometer pointer may move towards right or left, because the current can be in either direction. It deflects to right or left depending on direction of the electric current. Let us now perform the earlier activity in a different manner. There is a variation. As you can see, we do not have a magnet here in this setup. There are two coils, one is connected to a galvanometer and other is connected to a battery or a current source through a key. We wind the coils 1 and 2 of copper wire having large number of turns, say 150, means coil 1 has 100 turns, coil 2 has 50 turns, over a non-conducting roll. Here the roll is made up of a thick paper. Connect coil 1 with 100 turns in series with a battery and a plug key. This is shown in the diagram. Connect 2 with a sensitive galvanometer. This is the experimental setup you will need to perform this activity. Plug in the key and observe the galvanometer. You will find that there is a sudden deflection in the galvanometer in a particular direction. We have to note the deflection, means magnitude, as well as the direction. The galvanometer is seen to jump quickly and then return to 0, indicating that there is a momentary or current flowing for a very short duration in the coil 2. Coil 2 does not have a source of current, there is no cell, no battery, only detection mechanism, that is galvanometer, has been attached. But inserting key in the circuit of coil 1 produces current in coil 2. Now, you can think about the situation when we pass current in coil 1, The current produces magnetic field. The magnetic field through the coil increases from 0 to certain value, and this changing magnetic field is the cause of current. Now disconnect the current, disconnect the battery in the circuit, that is, you have to remove the key and observe the galvanometer again very carefully. You will now see that the deflection is momentary but in a direction opposite to that of the earlier situation when we plugged in the key. So pass the current, you get deflection or current. Stop the current, you again get deflection but now in opposite direction. So whether you increase the field from 0 to certain maximum or you decrease the field from maximum to 0, in both cases you get the current in coil 2. However, the direction of current is different. So we have observed that as soon as the current in coil 1 reaches a stationary value, the galvanometer in coil 2 shows no deflection. Means when the current is stationary, current is steady, the magnetic field is steady and the flow of current stops. Potential difference is induced as long as the magnetic field is actually changing, increasing or decreasing. As the current in coil 1 changes, the magnetic field associated with it also changes. A change in number of magnetic field lines around the secondary coil, that is coil 2, causes production of induced current in the coil. The process by which a changing magnetic field in a conductor induces current in another conductor is called electromagnetic induction. In practice, we can induce current in a coil either by moving the coil in a magnetic field or changing the magnetic field around it. It is convenient in most situations to move the coil in a magnetic field, and this method is widely used in production of electric current in electric generators. The schematic diagram of electric generator is on your screen. Based on phenomena of electromagnetic induction, the experiments studied above generate induced current, which is usually very small. We produce large current required for homes and industry by using the phenomena of electromagnetic induction through the device electric generator. In electric generator, mechanical energy, that is, we have to rotate the coil in a magnetic field, that is, input energy is mechanical energy. It produces electricity. Here are some problems for practice which are based on the phenomena of electromagnetic induction we have studied just now, and this next part is only for curious readers about Michael Faraday, who is regarded as the father of electricity. Thanks for being with us. Subscribe to our website and YouTube channel for further notifications. Should you have any feedback, you can write to the mail ID on your screen. Happy learning. Thanks a lot. You will get notification about further videos. We have to discuss the construction and working of an electric generator in subsequent videos.